We are Ascend NTNU from the Norwegian University of Science and Technology, and since being founded in 2015 we have developed autonomous drone platforms for multiple international competitions. With a proven track record of innovation and dedication, we're now setting our sights on the SUAS competition of 2024. This year's development team consists of 4 technical groups: hardware, perception, autonomy, and control, 2 non-technical groups, marketing and business, and a board that organizes the whole organization. Our competition teams consists of a team captain, safety pilot, backup safety pilot, ground control station operator, backup ground control station operator, 3 hardware, perception, and autonomy. Since participating in the previous SUAS competition, it has been the last year's goal of our team to further develop our technology and make a new drone to compete in the 2024 SUAS competition. It has been our main goal to design and build a custom UAV that can solve the specified tasks, introducing a carbon fiber hexacopter named after the sun-chasing god from Norse mythology, Skuld. The competition requirements were divided among the 4 technical groups, and each group was responsible for analyzing and providing concepts for solutions. Based on the SUAS rule set and different criteria for the various scenarios, we decided on acceptance criteria for the different parts of the challenge and general operational and safety requirements. Operation scenario. For the autonomous flight scenario, the following must be achieved. For the airdrop scenario, we have arrived at the following requirements. For the ODLC part, we must reliably detect, classify, and localize all standard and emergent objects within the airdrop boundary. Aircraft avoidance scenario. Skuld is a UAV hexacopter with its main body built from 2 custom-milled carbon fiber plates connected with aluminum brackets. The battery is located in the middle of the frame as the main battery for propulsion. To power the onboard electronics like the flight computer and sensors, a secondary low-voltage battery is used. Out from the main frame, there are 6 arms with overlapping carbon fiber propellers. In addition, the UAS consists of different subsystems, such as a custom-built drop-off mechanism for precise payload deployment and a gimbal with high-resolution camera, both located underneath the main frame. NVIDIA's Jetson Orin NX as the onboard computer to run the mission code. The flight controller is a Cube Orange running the open-source PX4 flight control software. It has a closed system that is responsible for both low-level control and advanced autonomous path planning, as well as communication to the ground control station. It receives waypoints and commands from the onboard computer to perform the mission. Additionally, it is connected to a remote ID receiver, 2 radio link modules and a long-range Wi-Fi module, as well as 2 GPS modules with the RTK support. Skuld can be monitored and controlled by a custom-built GCS that delivers a stable and reliable connection to the UAV. It features a high-brightness display and a rugged enclosure and has several hours of battery life. The camera used is the Autonomy IMX519 with a 25mm fixed focal length lens. It is connected with the MIPI CSI-2. Our focal length gives an average resolution of 200 x 200 pixels for a standard object when flying at 80 feet. The gimbal provides sufficient stabilization to ensure sharp images with minimal motion blur. The ODLC systems consist of 3 main parts: detection, classification, and localization. For detection, we use a YOLO V8 model with pre-trained weights that has been fine-tuned on custom data. Our dataset consists of synthetically generated images for the objects specified in the competition, created using Blender. The interface runtime is implemented with the NVIDIA Tensor RT framework to ensure high performance. In order to ensure high precision on small object detection, we slice each image into smaller parts and run the detection algorithm on each part separately in parallel. For the classification task, we developed our own network, which we call the ONET. It's heavily based on the well-known UNet in that both use an encoding-decoding pipeline to segment features and have binary masks as output. Our ONET, we use 2 encoders so that we can easily extract the shape and symbol separately. After doing so, we encode to a single output containing 2 binary masks for the shape and symbol color. Labeling a color simply from its RGB value on an image is a complicated task in itself, so we have a special solution for this as well, based on the fact that the rules provide a set of valid colors. From the binary masks that are the output of a UNet, we can use k-means clustering to extract a representative color. This is then transformed to the CLab color space, and we are then able to compute perceptual difference and label a color based on that value. To achieve successful localization, 2 things are necessary: the drone's position in a local ENU coordinate system and the camera's intrinsic parameters. The former is achieved with our RTK GPS system, while the latter is found using a checkerboard. With these in place, each detection can be projected to a familiar coordinate system. From all the detections, along with the confidence from our classification, we can create a discrete probability map. In the end, a Gaussian blur is applied to the map so that we can find optimal drop location. Deciding on a camera solution involved testing many different combinations of sensor, optics, cable, and mounting. We tested with 4 different cameras, focal lengths between 4 and 50 mm, USB and MIPI CSI, with and without shock absorption mounts, and lastly, with and without gimbal. Detection was largely trained and tested on synthetic data generated in Blender. then visually checking that we have few to none false positives and a majority of true positives during test flights and back data. Classification was mostly tested on hand-labeled images from a test flights, and localization was tested by flying over a single or 5 objects where we knew their position in the local coordinate frame, and then logging where the localization projects the objects and nothing where the water bottle lands. The payload includes 5 8-ounce water bottles that must be delivered carefully to the right airdrop boundary. To complete the mission, our team will begin by pre-attaching 2 out of the 5 water bottles, which will be dropped initially at their intended markers. Afterwards, a pit stop will be conducted to reload batteries and attach the last 3 water bottles. This allows Skull to execute the mission with a lighter payload and maximize the speed. The mechanism used to drop the payload consists of a spool of fishing line attached to the bottles with a clip-on mechanism and a shortened VLDC motor acting as an inductive brake. To release the payload, the teeth holding the spools in place are disengaged. When the water bottle touches down on the ground, the fishing line will disengage from the spool. This facilitates the separation of the payload in a controlled manner and ensures a careful, safe, and stable delivery of the payload. To ensure a fast and safe drop, a dual spool with 2 separate diameters are used. The last few meters of the spool is used on a smaller diameter to decrease the impact velocity. To determine the optimal drop speed, we tested a spool with a known diameter and calculated the drop speed by tracking the bottle on a video. Based on the calculated speed and assuming constant rotational velocity of the motor, we made a spool with 2 diameters. This way, we get the fastest possible drop with a safe impact. We have performed several airdrops at detected positions. The results shown are statistics of when Skull was detected, localized, and lowered the bottles all autonomously from the last 75 feet above ground. We have 2 main communication links between the ground and air. Firstly, we use a 2.4 GHz ELRS system for manual remote control. A TX16S radio controller with an external Radiomaster Ranger module is used on the ground, and a Radiomaster RP4TD is mounted on the UAV. The link is configured to 100 Hz with theoretical dBm sensitivity of -112 dBm. The maximum output power in Norway is 100 milliwatts, so this is what the max we have tested. But we run at 1 watt in the USA and expect a longer range. We have tested these modules with range shown in the diagram. We also use a motorized directional antenna for high bandwidth connections between the CGS and UAV. It consists of 2 5 GHz long-range Wi-Fi antennas, a dual-band bullet AC radio on the drone, and a directional ESO station AC mounted on a motorized stand. It uses GPS data to point in the right direction and connects to the UAS onboard computer. As our main telemetry link, the onboard computer routes MAVLink messages from the flight controller through this communication link to the ground. It gives us reliable, long-range connection to the UAV. As a backup telemetry connection, we use a 900 MHz RFD telemetry setup with a RFD 900X module on the ground control station and a RFD 900UX on the UAS. This link is independent of the onboard computer and is directly connected to the flight controller. They have been tested with the data shown. This is a visualization of our communication subsystem.
Here is the label diagram of our UAV Skull with its subsystems.
The airframe is constructed from 2 CNC milled carbon fiber plates. The arms of the frame are made out of carbon fiber tubes. Precision drill holes were made into the tubes using a manual milling machine. Most component mounts are 3D printed in PETG, including the drop mechanism. A custom connector for the arms has been developed for easy disassembling of the drone. The electronics for the drone are placed for effective cable routing and easy dismounting. In between the carbon fiber plates, we have the more permanent components, like the ESC and power distribution board for the high voltage side. On top of the drone, we have the smaller electronics mounted for easy access and troubleshooting. We designed our own circuit board for the low voltage side to fit our needs. It includes 2 buck converters to have both 5 volt and 12 volt rails. To ensure our onboard computer and other electronics don't need rebooting during the main battery swap, the 2 electrical systems are isolated from each other and use separate batteries. The drone uses an overlapping propeller design where every other propeller is mounted upside down. The overlap is around 13%, making for more compact design, while still being able to fly well and with good energy efficiency. Once Skull was deemed flight ready, we had to do an initial stability setup. This was done by tuning the basic PID controllers in the autopilot for altitude and position, and continued by tuning the trajectory parameters. Once we had a satisfactory tune, all the other tests could be performed, and we show the results here. The autopilot system used on Skull relies on the PX4 framework running on the Cube Orange. The Cube communicates with the autonomous systems running on the onboard computer via the Mavlink protocol. The PX4 autopilot system is capable of managing diverse flight scenarios, including tasks such as waypoint navigation, modified speed mode, and path rerouting. Additionally, we have our own autonomous system doing path planning, obstacle avoidance, and mission execution. The autonomous system runs on several ROS nodes, all in communication with a central deciding ROS node. The central ROS node takes decisions, while the other nodes perform services for the central deciding unit. This central node is designed as a push-down automation, a finite state machine with memory. The finite state machine has knowledge of the mission and is able to lead the drone through both ideal and unforeseen circumstances via a series of fail-safes and checks. In the preparation phase, mission coordinates are pushed to the onboard computer, where they are integrated into 3 distinct mission files: ingress waypoints, search boundary, and geofence border. When the ground control station deems that it is ready for the mission, it sets the drone into mission mode, and the onboard autonomous system handles all mission pushing navigation and path planning autonomously. During search, the autonomous systems monitors the drone's position and generates a heat map of where the drone has scanned, ensuring that the drone scans the entire search area. During the entire mission, an object avoidance module is continuously monitoring all remote ID messages received via Wi-Fi and Bluetooth, and if it predicts that its path is intersecting with another drone, it replans the path and pushes a new mission to the flight computer. The autopilot has undergone thorough testing both by setting waypoints manually and automatically. During testing, we switched seamlessly between different PX4 autopilot modes and completed whole mission runs autonomously. Adding to this, we have also tested the autopilot continuously throughout the year via our own simulator, custom built with Unity 3D game engine. On the Orin NX onboard computer, we have a ROS node continuously checking the received remote ID messages to detect whether there are any drones on an intersecting path with Skull. If another competitor drone is about to interfere with Skull's current path, the ROS node runs an RRT star search algorithm between the waypoints where the other drone intersects Skull's path. The algorithm aims to find the shortest path between the waypoints while avoiding the obstacle. If a path is found, the node runs a Bezier curve path smoothing algorithm on the path to smooth the flight and then overrides Skull's current planned path with a new one, avoiding the obstacle. If the algorithm deems it impossible to navigate between the 2 relevant points, which may happen if a drone is sitting on top of the waypoint we aim for, it sends an error message back to the main autonomous system, which handles it according to which mission component it is in. If the drone is in the search zone, it skips the waypoint. If it is in the ingress path, it waits for X seconds before pushing the same path again. If it is attempting to drop a payload, it selects another payload to drop, and if not, it waits for the drop point to become available. Due to hardware limitations of remote ID, we have implemented a fail-safe for if the drone finds itself in a situation where it is within the desired avoidance radius of another drone. If so, the algorithm moves the drone radially outward in order to avoid. Inside the drop zone, we have implemented an extra algorithm that checks the position of other drones compared to the position of the detected markers. If there are drones near the markers, the likelihood of the drone deciding to go to that marker drops. This is to keep distance from other drones to reduce the chances of any potentially dangerous scenarios. We have again continuously tested our autonomous systems in our in-house simulator. This is especially useful for scenarios such as obstacle avoidance, where it is difficult to get a realistic test of this in real life. The potential risk of failing to perform obstacle avoidance during testing in real life is also high. In the simulator, we could spawn however many competitor drones we wanted flying either directly after Skull, between markers, or back and forth scanning the drop zone. This made it easy to create realistic scenarios where other drones interfere with Skull's path, requiring object avoidance to avoid crashing into them. We could then rapidly test and iterate on our obstacle avoidance algorithm to improve it to a point where it successfully created a new set of waypoints and then avoided the other drones 1% of the time. A substantial amount of design suggestions came about during our brainstorming phase. both on the hardware and software sides. When it comes to the actual physical drone, the alternatives brought up were all discussed in light of us wanting to decrease size and weight and simply make the drone easier to work with. As an example, on the mechanical side, we ended up with overlapping propellers to make the design more compact. We did initial testing on a test stand with overlapping propellers. When we saw promising results of that, we set up our old drone with overlapping propellers to get more realistic data. A big decision that affected both mechanical and electrical was whether we wanted to make a pit stop to swap batteries or if we planned to do everything in a single flight. We ended up going for a pit stop solution, since our designs for swapping systems helped prevent human error, which is the main drawback. Had we not gone for this, we would have needed bigger batteries and therefore a heavier and more cumbersome drone. For the avoidance algorithm was between RRT star and A star. Despite A star guaranteeing optimality of the path, we found that RRT star's robustness, situational flexibility, and it outperforming A star in computational complexity made it a better choice. We concluded that finite state machines suit our needs better than our second choice, namely behavior trees. We found that FSM were the easiest theoretical framework to work with because the simplicity of FSMs reflect that of the mission structure. As this year's mission is alike the last year's in many ways, a lot of our safety procedures are heavily inspired by last year's. All our members are made aware that we are working on a very big drone that flies with great speeds and that each step should be taken very cautiously. Our control and hardware groups are the ones doing the work on the physical systems on the drone. All members in these groups go through courses and training to learn how to use tools and machinery in a safe way and are obligated to ensure that the motors on the drone are powered off when working. Other than constant awareness of working with dangerous equipment, we have more concrete safety measures both while developing and testing the drone. When testing, everything we do is said out loud and we ensure that no one is in the immediate vicinity of the drone as it's being armed. Our flights are all done in an airfield with well-defined boundaries and safety nets in place. When it comes to in-flight operations, the hexacopter design of the drone allows for motor redundancy, meaning that if a motor were to fail, it can still manage to have a safe landing and not crash uncontrollably. All our pilots have drone flying licenses and go through a lot of flying with bigger and smaller drones, as well as in simulators, so as to ensure that they are competent enough to take over should anything happen. Despite this, should there be an emergency, the drone and controller are equipped with an independent kill switch that cuts all power to all motors. When it comes to the drop-off systems, the release speed is tested so that it never gets to the point where it could be dangerous to anyone in the vicinity. When we're content with how our systems work together and the integration in our in-house simulator, we go to Uddevol, a model airplane airfield. We have predefined packing checklists for all our tests that have to be completely filled out before we leave. Once everything is set up in the site, we don't immediately start flying a mission. Rather, we test that the communication with the drone is up and running, ensure that we have good GPS positioning and heading, after which we do a simple test to ensure that all propellers are spinning. When all these basics are in place, the actual testing can begin. The mission is defined in Q ground control on our ground control station, and our operator is constantly monitoring the telemetry data. The pilot is prepared to take over at all times and follows the drone's movements closely. During testing, the data from the drone is logged for off-site analysis to see what can be improved for the next runs. In this video, we have described our latest UAV Skull and its ground control station for mission control. We have introduced our team of 2024 and our competition team. We have covered the requirements derived from the rules and targets of the competition and presented our solutions for handling these different challenges. This includes dozens of technical solutions and essential operational procedures and principles for ensuring that we fly safely while hitting our performance targets. Then importantly, we have gathered the numbers and necessary documentation and statistics to present what our UAV is capable of. We have shown that it flies safely, as demonstrated by a proof of safe flight and relevant performance metrics. We are very proud of our achievement, and it has been a great learning experience to create such complex systems. We have worked several hours, collaborated across different disciplines in our internal groups, and together grown as a team. We look forward to seeing the solutions other teams have come up with and to compete against them this summer. We are Ascent NTNU. Thank you for your attention.